Hello, friend. Welcome to another quiet journey through the cosmos. Tonight we'll drift somewhere strange, somewhere small, somewhere that exists at the very edge of what distance even means. Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to itself. But tonight, we're going the other way. Not outward into the endless dark, but inward. Down past the skin, past the cells, past atoms and quarks. Down to a place where the universe whispers a secret it never tells loudly. A place where space itself stops being space. Where distance becomes something else entirely. A place called the Planck length. Before we begin, if you find comfort in these quiet journeys, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Now, let's drift. Imagine holding your hand in front of your face. The distance between your fingers and your eyes may be a foot, maybe less. That distance is real. You can feel it. You can measure it. Now imagine the distance between Earth and the Moon, 250,000 miles of emptiness that light crosses in just over a second. That distance is real too, though you'll never walk it. Now go smaller. The width of a human hair, about 70 micrometers. The size of a red blood cell, 7 micrometers. A bacterium, 1 micrometer. An atom, 1/10 of a nanometer. Scientists suggest that at each step down, we're descending into worlds we cannot see but can still measure, still understand, still touch with our instruments and mathematics. But what happens when you keep going? What happens when you try to measure smaller and smaller distances until you reach some final limit? What happens when the ruler itself breaks down? This is where the Planck length lives. At 1.6 times 10 to the negative 35th meters. It's a number so small that if you tried to write it out, you'd need to put 34 zeros after the decimal point before you reach the 1. If an atom were the size of the observable universe, the Planck length would still be smaller than a human cell. It's the distance at which research shows the very fabric of space-time begins to tremble and fold and lose all meaning. Some believe this is the shortest length that has any physical significance in our universe. Not because there's some tiny wall we hit, but because below this scale, the classical idea of distance, the smooth continuum we walk through every day, dissolves into something we can barely imagine. Quantum foam, some call it. A churning, bubbling mess where space and time are no longer separate things, where geometry itself shivers and breaks apart. You don't need to understand everything. Just rest and let curiosity do the listening. The Planck length isn't just a measurement. It's a doorway, a threshold between the universe we think we know and the universe that hides beneath it. Most people have never heard of it. It doesn't appear in everyday life. You'll never measure it with a ruler. You'll never see it through a microscope. Even our most powerful particle accelerators machines that smash protons together at nearly the speed of light can't come close to probing distances this small. To see the Planck length directly, scientists suggest you'd need an accelerator the size of the Milky Way galaxy. So, why does it matter? Because embedded in this impossibly tiny number are 3 of the most fundamental constants in all of physics. The speed of light, which governs how fast information can travel through the universe. The gravitational constant, which tells mass how to bend space. And Planck's constant, the quantum of action, the heartbeat of uncertainty itself. These 3 numbers, woven together through a simple equation, define a length scale that represents the meeting point of gravity and quantum mechanics. The 2 great theories that describe our cosmos, but refuse stubbornly beautifully to speak the same language. It's as if the universe left a fingerprint at the smallest possible scale. A signature written in constants numbers that don't change no matter where you are, no matter when you measure them. Light always moves at the same speed. Gravity always pulls with the same strength per unit mass. The quantum world always flickers with the same fundamental uncertainty. And when you combine them, They point to a distance so small, it almost feels like a joke, a cosmic whisper saying, "This far and no further." But here's the thing. The Planck length isn't a wall. It's not a brick at the bottom of reality. It's more like a horizon, a place where our maps stop working, where the equations we trust, the smooth curves of Einstein's space-time, and the probabilistic waves of quantum mechanics both begin to scream at each other. It's the edge of what can be known, the place where physics itself starts to dream. Think about it this way. When you look at a beach from far away, the sand seems smooth, continuous. You could walk across it and feel like you're gliding over a solid surface. But get closer, crouch down. Look at individual grains. Suddenly, the beach isn't smooth at all. It's made of tiny pieces, each one separate, each one distinct. Now, imagine going even closer. Imagine somehow zooming in past the grains, past the molecules of silicon dioxide, past the atoms, past the nucleus, past the quarks inside the protons. Keep going, keep descending. Eventually, some believe you'd reach a scale where even the concept of closer stops making sense, where space itself is no longer a smooth sheet, but a granular, foamy, chaotic sea. That's the Planck scale, and the Planck length is the size of those grains, if grains is even the right word. At that scale, research shows the energy density becomes so high that tiny black holes could flicker in and out of existence. Space-time could twist into loops and knots. Cause and effect might blur. The past and future might lose their order. It's not that we know this happens. It's that our best theories whisper that it must. But we're getting ahead of ourselves. To understand the Planck length, we need to go back. Back to the man who never intended to find it. Back to a physicist in Berlin at the turn of the 20th century, staring at a problem about light and heat, trying to make sense of something that didn't make sense. A man named Max Planck. He wasn't looking for the smallest distance in the universe. He was just trying to explain why hot objects glow the way they do. But in solving that problem, he stumbled onto something far stranger. He found a constant, a number, that described the graininess of energy itself, and from that constant buried inside the equations emerged a length. The length. The Planck length. It's strange, isn't it? How the biggest discoveries often come from the smallest questions. How trying to understand the warmth of a coal fire led to the realization that the universe has a smallest meaningful distance. How a man working alone with mathematics and thought experiments ended up touching the very fabric of reality. Max Planck didn't set out to rewrite the universe. He just wanted his equations to work. But sometimes it seems as though the universe reveals itself to those who listen carefully enough. And that's where we'll go next. Into the life and mind of Max Planck. Into the problem that obsessed him. Into the moment when he realized that energy, that light itself couldn't be divided forever. That there was a smallest step, a quantum, and that this quantum implied something profound about the nature of space and time. He didn't call it the Planck length at first. That name came later from other physicists who saw what he'd done and realized its implications. But the seed was planted, the idea was born, and once born, it couldn't be unborn. So, let's drift together into that story, into the quiet revolution of a man who measured the invisible. Berlin, 1900, a city humming with gaslight and ambition, where cobblestone streets echoed with the clatter of horse-drawn carriages and the whispers of a new century about to begin. In a modest office at the University of Berlin, a 42-year-old physicist sat alone with a problem that wouldn't let him sleep. His name was Max Planck, and he was about to crack open the universe without meaning to. Planck wasn't trying to find the smallest distance in existence. He wasn't even thinking about distances at all. He was thinking about light. Specifically, he was thinking about why hot objects glow the way they do. Why a piece of iron, when heated, first glows red, then orange, then white. Why the color shifts as the temperature rises. It seems like such a simple question, doesn't it? the kind of thing you might notice while staring into a fireplace on a cold winter night. But in 1900, this simple question was tearing physics apart. Scientists at the time called it the ultraviolet catastrophe. The problem was this: according to classical physics, according to everything physicists thought they understood about energy and waves, a hot object should emit infinite energy at high frequencies. A glowing coal fire should be blasting out deadly amounts of ultraviolet and X-ray radiation. But it doesn't. You can sit by a fire and feel warm, not incinerated. The equation said one thing, reality said another. And Max Planck, a man who believed deeply in the power of mathematics, couldn't let that contradiction stand. For years, he tried to fix it using classical physics. He adjusted equations, tweaked assumptions, searched for loopholes. Nothing worked. The math kept predicting catastrophe. The world kept refusing to comply. So, in October of 1900, Planck did something desperate, something he would later call an act of desperation. A lucky guess, a mathematical trick that he didn't truly believe in. He proposed that energy wasn't continuous, that light, that radiation couldn't be divided infinitely, that there was a smallest possible chunk of energy, a quantum, and that this quantum was proportional to the frequency of the light. The higher the frequency, the bigger the quantum. And at very high frequencies, the quanta became so large that they simply couldn't be emitted. The catastrophe vanished. The equations worked. The universe made sense again. But Planck himself didn't believe it. Not really. He thought it was a mathematical sleight of hand, a temporary patch until someone smarter came along with a better answer. He presented his work to the German Physical Society on December 14, 1900, a date that would later be remembered as the birthday of quantum mechanics. But on that day in that room, most physicists politely nodded and moved on. It seemed too strange, too radical. Energy came in chunks. Light was grainy. It didn't feel right. It didn't match the smooth, continuous world they lived in. What Planck had discovered, though, he couldn't see it yet, was a fundamental constant of nature, a number that described the graininess of action itself. He called it H. Planck's constant. Its value is 6.6 times 10 to the negative 34th joule seconds, a number so small it barely registers in the everyday world. But at the quantum scale, research shows it governs everything. It determines the size of atoms, the color of stars, the structure of molecules. It's the reason chemistry works, the reason you don't fall through the floor, the reason light behaves like both a wave and a particle. And hidden inside this constant waiting to be discovered was a length. Not just any length, the Planck length. But Planck himself didn't find it right away. That realization came later, as he and other physicists began to explore what his constant really meant. They realized that you could combine Planck's constant with two other fundamental constants, the speed of light and the gravitational constant. And from those three numbers alone, you could construct natural units of measurement. Units that didn't depend on human choices, like meters or seconds or kilograms. Units that were built into the fabric of the universe itself. The Planck length was one of those units. It emerged from the mathematics like a ghost, a distance scale so small that it represented the meeting point of quantum mechanics and gravity. At this scale, scientists suggest the uncertainty principle becomes so extreme that the very concept of distance starts to wobble. Space itself becomes quantum. It flickers and foams. It stops being the smooth stage on which events unfold and becomes something stranger, something more alive. But here's the beautiful irony. Planck himself never fully accepted the quantum revolution he'd started. For decades, even as younger physicists like Einstein and Bohr and Heisenberg ran wild with quantum ideas, Planck remained cautious, skeptical, hoping that somehow classical physics could be restored. He was a conservative man, deeply religious, a lover of order and harmony. The idea that the universe was fundamentally grainy, fundamentally uncertain, troubled him. He wanted the world to make sense in the old way. He wanted smooth curves and predictable outcomes. In 1918, Planck won the Nobel Prize for his discovery of the quantum of action. By then, the quantum revolution was unstoppable. Young physicists were rewriting the rules of reality, discovering that particles could be waves, that observation changed outcomes, that the universe at its smallest scales was a place of probability rather than certainty. And Planck, the man who'd started it all, watched from the sidelines, respected, but no longer leading a reluctant prophet of a new age. There's a lesson in that, isn't there? Sometimes the most important discoveries come from people who don't want to believe them. Sometimes the universe reveals itself to those who are simply trying to make the math work, to reconcile observation with theory, to solve a problem that won't go away. Planck didn't set out to discover that space has a smallest meaningful distance. He set out to explain why a piece of hot metal glows red instead of violet. But one question led to another and another until he touched something fundamental. The Planck length 1.6 times 10 to the negative 35th meters isn't something Planck ever saw or measured. It's a prediction, a consequence of his constant combined with the speed of light and the strength of gravity. It's a number that suggests the universe has a built-in resolution, a pixel size below which the smooth fabric of space-time dissolves into quantum uncertainty. And it all began with a man in Berlin staring at the glow of heated metal, refusing to accept that the equations were wrong. Think about that for a moment. How many times do we dismiss our own strange ideas because they don't fit what we expect? How many times do we ignore the whisper of something new because it makes us uncomfortable? Planck spent years resisting his own discovery. He called it a desperate measure. He hoped someone would prove him wrong. But the universe had other plans. The universe, it seems, doesn't care much about our comfort. It simply is what it is. Grainy, uncertain, beautiful in its strangeness. Another common mistake people make is thinking that the Planck length is the size of the smallest particle, that there's some tiny ball of matter exactly one Planck length wide sitting at the bottom of reality. But that's not quite right. The Planck length isn't a particle, it's a distance. It's a scale at which our current theories break down, where quantum mechanics and general relativity both try to speak at once and end up shouting gibberish. It's the edge of the map, not the floor of the dungeon. Below that scale, we don't know what happens. Maybe space is discrete, made of tiny loops or strings or something else entirely. Maybe it's still continuous, but in a way we can't yet describe. The Planck length is a question mark written in the language of constants. Planck died in 1947 at the age of 89, having lived through 2 world wars and the complete transformation of physics. He saw his constant become the foundation of quantum mechanics. He saw it used to explain atoms, molecules, the behavior of light, the structure of matter. He saw it give birth to technologies he could never have imagined, from transistors to lasers to the computer you might be listening to this on. But he never saw anyone measure the Planck length directly. He never saw anyone probe the quantum foam. He never saw the confirmation of the deepest implications of his work. And maybe in a way that's fitting. Some truths are too small to touch. Some answers live only in the mathematics whispered between constants, hidden in the structure of the laws themselves. What Planck gave us wasn't just a number, it was permission. Permission to imagine that the universe might be stranger than it appears. Permission to trust the math, even when it leads somewhere uncomfortable. Permission to ask what happens when you push a question as far as it can go. And from that permission, from that willingness to follow an equation into the dark, emerged a vision of reality that we're still trying to understand. So, here's a question for you. If you could ask Max Planck one thing, knowing what we know now, what would it be? Would you ask him if he ever imagined that his constant would reveal the smallest meaningful distance in the universe? Would you ask him how it felt to start a revolution he didn't believe in? Would you ask him if he ever made peace with the quantum world? Maybe he'd smile that quiet, thoughtful smile and say that the universe doesn't ask for our belief. It simply asks for our attention. And speaking of attention, there's something else waiting in those constants. 3 numbers woven together, pointing to a distance almost too small to imagine. We've met Planck's constant born from the glow of heated metal. But what about the other two? What about the speed of light, the cosmic speed limit, and the gravitational constant, the measure of how mass bends space? These three numbers, each discovered in vastly different ways, each describing vastly different phenomena, somehow fit together like pieces of a puzzle we didn't know existed. And when you combine them, when you let them speak to each other through the language of mathematics, they reveal something profound. They reveal the trinity of constants that define the Planck length, and with it the very fabric of space-time itself. Three numbers, three seemingly unrelated discoveries separated by centuries and continents. Three constants that describe three different aspects of reality. And yet, when you bring them together, when you let them dance in the same equation, they reveal something extraordinary. They point to a distance so fundamental, so deeply woven into the fabric of existence that it feels less like a measurement and more like the universe naming itself. The first constant is the one we've already met. Planck's constant h equal to 6.6 times 10 to the negative 34th joules seconds. Born from the glow of heated metal in 1900, it describes the graininess of energy, the quantum of action, the heartbeat of uncertainty that pulses through every atom, every photon, every particle in existence. Without it, atoms would collapse, chemistry would fail, and the universe as we know it would unravel into impossible configurations. It's the signature of the quantum world, the number that says energy doesn't flow smoothly, but arrives in discrete packets like raindrops instead of a continuous stream. The second constant is perhaps the most famous number in physics. The speed of light c equal to 299,792,458 meters per second, often rounded to 300 million meters per second for simplicity. This is the cosmic speed limit, the fastest that anything, matter or information or causality itself can travel through space. Scientists suggest it was first measured with precision by Danish astronomer Ole Romer in 1676, not by racing light directly, but by watching the moons of Jupiter. He noticed that the eclipses of Jupiter's moon, Io, seemed to arrive late when Earth was moving away from Jupiter, and early when Earth was moving toward it. The delay was caused by light taking time to cross the changing distance. From that pattern, Romer calculated that light had a finite speed, roughly 220,000 kilometers per second by his estimate. Not perfect, but astonishingly close for the 17th century. But it was Albert Einstein in 1905 who elevated the speed of light from a mere measurement to a fundamental principle. In his special theory of relativity, Einstein proposed that the speed of light in a vacuum is the same for all observers, regardless of how fast they're moving. It doesn't matter if you're standing still or racing toward a beam of light at half the speed of light yourself. The light still passes you at exactly c. This strange, counterintuitive fact reshapes space and time. It means that time can slow down, that lengths can contract, that simultaneity is relative. The speed of light isn't just a speed. It's the conversion factor between space and time, the thread that weaves them into a single fabric called space-time. The third constant is more subtle, more mysterious. The gravitational constant g equal to 6.67 times 10 to the negative 11th cubic meters per kilogram per second squared. This number describes the strength of gravity, the attractive force between masses. It tells you how much a kilogram of matter will pull on another kilogram of matter across a given distance. Without g, there would be no planets, no stars, no galaxies. Matter would drift in isolation, never clumping, never collapsing, never igniting into the fusion fires that light the cosmos. The story of G begins with Isaac Newton in 1687. In his Principia Mathematica, Newton proposed that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. It was a beautiful, simple law. But Newton didn't know the constant of proportionality. He didn't know the actual strength of gravity. That had to wait until 1798, when English scientist Henry Cavendish performed one of the most delicate experiments in the history of physics. Using a torsion balance, a device so sensitive it could detect the gravitational pull between two lead spheres in a laboratory, Cavendish measured G for the first time. He called it weighing the Earth, because once you know G, you can calculate the mass of the planet from the strength of gravity at its surface. But here's the strange thing. Of all the fundamental constants, G is the one we know least precisely. Even today, with all our technology, our lasers and atomic clocks and quantum sensors, G remains elusive. Different experiments give slightly different values, and scientists still argue about the exact number. It's as if gravity, the force we experience most directly, the force that keeps our feet on the ground, is also the one that hides its true strength most carefully. So, we have three constants. Planck's constant from quantum mechanics, describing the microscopic, the speed of light from relativity, describing motion and space-time, the gravitational constant from Newton and Einstein, describing how mass shapes the universe. Three pillars of physics, each discovered independently, each solving a different puzzle. And yet, when Max Planck and later physicists combined them, something remarkable emerged. You can take these three numbers, multiply, and divide them in just the right way, and out pops a length. The Planck length. The equation is simple, almost elegant. The Planck length equals the square root of Planck's constant times the gravitational constant divided by the speed of light cubed. Let that sit for a moment. Three constants that have nothing obvious to do with each other, that were discovered in completely different contexts, that describe wildly different phenomena, all come together to define a distance. And not just any distance. The smallest distance that has any physical meaning in our current understanding of the universe. It's as if the universe has a built-in ruler, and the tick marks on that ruler are written in the language of H, C, and G. Research shows that the Planck length, approximately 1.6 times 10 to the negative 35 meters, represents the scale at which quantum effects of gravity become important. At distances larger than the Planck length, you can treat space-time as smooth, just like Einstein did. Gravity bends it gently, predictably. But at the Planck scale, quantum mechanics intrudes. Space-time itself becomes uncertain, jittery, foamy. The smooth geometry breaks down. You can't talk about precise positions or smooth trajectories anymore. Everything becomes probabilistic, fluctuating, strange. Here's where a common misunderstanding arises. Some people hear about the Planck length and imagine it's the size of some fundamental particle, some ultimate building block. They picture tiny Planck-sized spheres stacked together like cosmic Lego bricks. But that's not quite right. The Planck length isn't the size of a thing. It's the scale at which our descriptions of space break down. It's not that there's a smallest piece of space. It's that below this scale, the very concept of space, as we understand it, smooth, continuous, measurable, stops making sense. It's a boundary of knowledge, not a boundary of existence. Think of it this way. Imagine you're trying to measure the position of an electron. Quantum mechanics tells you there's a fundamental limit to how precisely you can know both its position and its momentum at the same time. That's the Heisenberg uncertainty principle. Now imagine trying to measure a distance smaller than the Planck length. To do that, you need to use a probe with a wavelength shorter than the Planck length, but a shorter wavelength means higher energy thanks to Planck's constant. And at the Planck scale, scientists suggest the energy becomes so high that it would create a gravitational field strong enough to curve space-time drastically. You'd essentially create a tiny black hole with your measurement. The act of measuring would destroy the thing you're trying to measure. The universe, in effect, refuses to let you look that closely. This is why the Planck length is sometimes called the quantum of space. Not because space is literally made of Planck-sized chunks, but because it represents the resolution limit of reality itself. Below that scale, our current theories, quantum mechanics and general relativity, both fail. They give nonsensical answers, infinity's contradictions. They stop talking to each other. And in that silence, in that gap between theories, lies one of the great mysteries of modern physics. The beauty of the Planck length is that it emerges naturally from the constants. You don't have to invent it or force it. It just appears when you combine h, c, and g. It's as if the universe left a clue hidden in plain sight, waiting for someone to notice. And the clue says this there is a scale where quantum mechanics and gravity must meet, where the wave-like nature of particles and the curvature of space-time must somehow reconcile. We don't yet have a theory that works at that scale. String theory tries, loop quantum gravity tries, other approaches try, but none of them are proven. None of them are tested. The Planck scale remains for now beyond our reach. But here's what we can say. The Planck length is approximately 10 to the 20th times smaller than a proton. To put that in perspective, imagine shrinking a proton down to the size of the Planck length. The ratio is about the same as shrinking the observable universe down to the size of a large tree. That's how many orders of magnitude we're talking about. It's a distance so small that if you tried to count Planck lengths across the width of a human hair, you'd need a number with about 25 digits, 25 zeros. It's almost incomprehensible. And yet, some believe this incomprehensibly tiny scale might hold the key to understanding everything. Because if space-time is quantum at the Planck scale, then the Big Bang, the very birth of the universe, happened at energies and densities where Planck scale physics dominated. The first moments of the cosmos, the first fraction of a second, were governed by rules we don't yet fully understand. To truly know where we came from, to truly grasp the origin of space and time, and matter and energy, we need to understand what happens at the Planck length. Einstein spent the last decades of his life searching for a unified field theory, a single framework that would merge gravity and electromagnetism and the quantum. He never found it. He died in 1955, still searching, still scribbling equations, still hoping. But maybe he was looking in the right place. Maybe the unification he sought lies at the Planck scale, where the constants he helped discover the speed of light and the gravitational constant meet the constant. He initially doubted Planck's h, and together whisper a truth we're only beginning to hear. Have you ever wondered why these three constants have the values they do? Why is the speed of light exactly 299,792,458 meters per second? And not something else? Why is Planck's constant 6.6 times 10 to the negative 34 and not 10 times larger or smaller? Why is gravity so much weaker than the other forces with g being such a tiny number? These aren't questions physics can answer yet. We measure the constants, we use them. But we don't know why they are what they are. Some theories suggest there might be deeper principles, deeper symmetries that fix these values. Others suggest our universe might be one of many each, with different constants, and we happen to live in one where the constants allow for atoms, stars, and life. A kind of cosmic selection effect. But whatever the reason, these three numbers, h, c, and g, define the Planck length. And the Planck length in turn defines a boundary, a horizon beyond which our current understanding fades into speculation. It's humbling, isn't it, to realize that with all our knowledge, all our technology, all our mathematics, there's still a scale of reality we can't touch, can't probe, can't fully comprehend. A scale where the rules change, where space and time might not even be fundamental but emergent, built from something deeper, something stranger. The lesson here is subtle but profound. The universe doesn't care about our categories. It doesn't respect the boundaries we draw between quantum mechanics and gravity, between the very small and the very large. At the Planck scale, those boundaries dissolve. And maybe that's the point. Maybe the Planck length exists to remind us that reality is more unified than it appears. That the quantum world and the gravitational world, the world of particles and the world of curved space-time, are not separate realms, but different faces of a single underlying truth. A truth written in constants, whispered through equations, waiting patiently for us to listen. And if we listen carefully, if we follow the mathematics down to its smallest implications, we find ourselves standing at the edge of something astonishing. A number so small it defies imagination, yet so fundamental it touches everything. 1.6 times 10 to the negative 35 meters. The Planck length, where three constants converge and the universe begins to reveal its deepest grammar. Numbers can be deceptive. We use them every day without really feeling their weight. A million sounds large until you compare it to a billion. A nanometer sounds small until you realize a virus is about 100 nanometers wide and still too large to see with your naked eye. But some numbers exist in a realm so extreme that our minds simply can't hold them. They slip through our thoughts like water through open fingers. 1.6 times 10 to the negative 35 meters is one of those numbers. Let's begin where we are. You sitting or lying down, listening to these words. Your body is roughly 1.7 meters tall, give or take. That's our starting point. Human scale. The scale of breath and heartbeat, and the space between your hand and the wall. Now, let's descend. Let's journey inward, step by step, each step taking us into a world, stranger and smaller than the last, until we reach the very edge of meaning itself. First, stop the width of a human hair, about 70 micrometers, 70 millionths of a meter. You can barely see it if you hold it up to the light, a thin golden thread against the sun. It feels small, but we've barely begun. Divide that hair by 10 and you're at the size of a typical human cell, about 7 micrometers across. The building blocks of your body invisible to the eye, but teeming alive, breathing oxygen and burning glucose and dying and being replaced every moment of your life. Go smaller still. Divide by 1,000 and you reach the scale of bacteria. About 1 micrometer, 1 millionth of a meter. A bacterium is a single cell simpler than yours, but still astonishingly complex. It has a membrane protein's DNA molecular machinery that spins and pumps and reads genetic code. It's an entire world, and you could fit thousands of them on the head of a pin. But we're not stopping here either. Shrink down another factor of 10,000 and you've reached the scale of a virus. About 100 nanometers, 100 billionths of a meter. At this scale, scientists suggest you're approaching the boundary between life and chemistry. A virus isn't quite alive. It can't reproduce on its own. It's more like a molecular machine, a packet of genetic instructions wrapped in protein, waiting to hijack a cell. And yet, it's real. It exists. It can change the world. A virus this small brought entire civilizations to their knees throughout history, invisible enemies that no one could see until the 20th century. Keep shrinking. Divide by 1,000 again, and you reach 10 nanometers the size of a large protein molecule. Proteins are the workhorses of life, folding into intricate shapes to catalyze reactions, carry signals, build structures. At this scale, you're no longer looking at things in the traditional sense. You're looking at shapes made of atoms, chemical bonds holding matter together in specific geometries. There's no color here. Color comes from light interacting with matter, and at this scale, visible light wavelengths are too large to resolve details. Everything is shadows and electron clouds. Now, we reach the atom, about 1/10 of a nanometer, 1 angstrom 10 to the negative 10 meters. This is the scale of chemistry of bonds forming and breaking of electrons orbiting nuclei. An atom is mostly empty space, research shows. If you could magnify an atom to the size of a football stadium, the nucleus would be a grain of rice sitting at the center, and the electrons would be tiny specks orbiting somewhere in the upper seats. Everything in between all that space is just probability fields, regions where electrons might be found if you looked. But we're not done. Not even close. Shrink down another 100,000 times and you reach the nucleus of the atom, about 10 femtometers 10 to the negative 15 meters. The nucleus is where almost all the mass of an atom lives, packed into an incredibly dense cluster of protons and neutrons. A nucleus is held together by the strong nuclear force, one of the 4 fundamental forces of nature. and it's powerful enough to overcome the electromagnetic repulsion between positively charged protons. Without it, atoms would fly apart. Matter would not exist. And inside the nucleus, protons and neutrons, which are themselves made of quarks. Quarks are fundamental particles, as far as we know. They're not made of anything smaller. A quark is about 10 to the negative 18 meters, though that's a bit misleading, because quarks don't really have a size in the classical sense. They're point-like particles, or at least they behave that way in our experiments. When physicists at CERN smash protons together at nearly the speed of light, they're probing distances down to about 10 to the negative 19 meters, trying to see if quarks have any internal structure. So far, research shows they don't. They seem to be truly fundamental. But we're still not at the Planck length, not even close. From the scale of a quark, you'd need to shrink down another 10,000 trillion times to reach the Planck scale, 10 to the negative 35 meters. 1.6 followed by 34 zeros after the decimal point. It's a number so small that if you tried to count Planck lengths across the width of a proton, you'd need about 10 to the 20th of them. That's 100 billion billion. If a single Planck length were the size of a grain of sand, a proton would be about the size of the Milky Way galaxy. Let that image settle. The Milky Way, 100,000 light years across, containing hundreds of billions of stars. And a proton, a particle so small, you need powerful microscopes even to detect its effects. The ratio between them. That's the ratio between a proton and the Planck length. It's almost obscene in its extremity. It breaks the imagination. It makes the mind go quiet. Here's another way to think about it. Imagine you could zoom in on a single atom and enlarge it to the size of the entire observable universe. That universe is about 93 billion light years across a distance so vast, it takes light 93 billion years to traverse it, though the universe itself is only about 13.8 billion years old, because space has been expanding faster than light can cross it. Now, in this atom-sized universe, the Planck length would still be smaller than a human cell. That's the scale we're talking about. That's the chasm between the everyday world and the Planck world. Why does this matter? Because at the Planck scale, scientists suggest the very nature of space-time changes. At larger scales, space feels smooth. You can move continuously from one point to another. You can measure distances with arbitrary precision, at least in principle. But at the Planck length, quantum mechanics intrudes violently. The uncertainty principle tells us that the more precisely you try to locate something, the more uncertain its momentum becomes. And at the Planck scale, that uncertainty becomes so extreme that it creates energy fluctuations powerful enough to warp space-time itself. Imagine trying to measure a distance of 1 Planck length. To do that, you'd need to use a probe, perhaps a photon, with a wavelength of about 1 Planck length. But the energy of a photon is inversely proportional to its wavelength. Shorter wavelength means higher energy. A photon with a Planck scale wavelength would have what's called the Planck energy, about 10 to the 9th joules. That's roughly the energy of a car traveling at highway speed, concentrated into a single particle. And when you concentrate that much energy into a region of space, 1 Planck length across, research shows the energy density becomes so high that it curves space-time into a tiny black hole. The very act of measuring destroys the measurement. The universe refuses to be examined at that scale. This is why the Planck length is sometimes described as the pixel of reality. Not because space is literally pixelated, made of discrete chunks, but because below that scale, the concept of space as we know it, smooth, continuous, measurable, breaks down completely. It's a horizon of knowledge. Beyond it, our current theories give nonsensical answers. Infinities appear, causality tangles. The smooth geometry of Einstein's space-time and the probabilistic haze of quantum mechanics collide and refuse to reconcile. There's a common mistake people make when they first hear about the Planck length. They imagine it's the size of some ultimate particle, some smallest piece of matter sitting at the bottom of the cosmic hierarchy. They picture reality as a grid with Planck-sized cells and everything moving from cell to cell in discrete jumps. But that's not quite right. The Planck length isn't a building block, it's a boundary, a signpost that says, here the rules change, here we don't know what happens. It's the edge of the map where the cartographers stopped drawing because the territory became unmappable. Some theories do propose that space might be discrete at the Planck scale. Loop quantum gravity, for instance, suggests that space-time is woven from tiny loops, each about a Planck length in size, connected in a vast network. In this picture, space isn't continuous but granular, like a fabric made of threads. Other theories, like string theory, propose that fundamental particles are actually tiny vibrating strings, and those strings are about a Planck length long. In this picture, the Planck length is the size of the most basic objects in the universe. But these are still just theories, mathematical frameworks we've constructed to try to understand what might be happening at that scale. We have no experimental evidence. We have no direct observations. We have only mathematics, intuition, and hope. What we do know, what the numbers tell us unambiguously, is that the Planck length represents the meeting point of three fundamental aspects of reality: quantum mechanics encoded in Planck's constant, relativity and the structure of space-time encoded in the speed of light, and gravity, the curvature of space by mass encoded in the gravitational constant. Thus, three aspects which normally operate in separate domains collide at the Planck scale. And when they collide, something strange happens. Space itself becomes quantum. It fluctuates, it trembles. It's no longer the passive stage on which events unfold, but an active player seething with energy, creating and destroying virtual particles, warping and twisting in ways we're only beginning to imagine. Think about the journey we've just taken. From your body, 1.7 meters tall, down through cells and bacteria and viruses and molecules and atoms and nuclei and quarks down, through 17 orders of magnitude, and then another 16 orders of magnitude beyond that to reach the Planck length. That's 33 orders of magnitude total, 33 factors of 10. It's a number so far removed from human experience that we can only approach it through metaphor and analogy and the cold precision of mathematics. And yet this unfathomably tiny distance might be the key to understanding the universe at its largest scales. Because the Big Bang, the event that birthed space and time and matter and energy, began at energies where Planck scale physics dominated. In the first 10 to the negative 43 seconds of the universe's existence, the so-called Planck epoch, everything we know was compressed into a region where quantum gravity reigned. To understand the origin of the cosmos, we need to understand what happens at the Planck length. The smallest and the largest, the beginning and the boundary, are intimately connected. There's a lesson in that. Isn't there? Scale matters, but not in the way we usually think. The Planck length isn't important because it's small. It's important because it's where different aspects of reality meet, where quantum mechanics and gravity too, theories that describe the universe so well in their separate domains, must somehow speak the same language. And they don't. Not yet. That's the puzzle. That's the challenge facing physicists today. How do you reconcile the smooth, deterministic curvature of space-time with the jittery, probabilistic quantum foam that seems to lurk beneath it, 1.6 times 10 to the negative 35 meters? A number that breaks imagination. A distance that can't be measured, can't be seen, can't be directly probed with any technology we can envision. And yet it's real. It's written into the constants of nature. It emerges from the deepest laws of physics. It's the whisper of something fundamental, something true, something waiting at the edge of what we can know. And if we could somehow look that closely, if we could peer into the Planck scale foam, what would we see? Would we see loops of space-time, vibrating strings, something else entirely? Or would we find that the question itself doesn't make sense, that seeing and measuring and knowing all break down at that scale, leaving only mathematics and mystery? That mystery is where we're headed next. Into the foam, into the quantum trembling of space-time itself, into a vision of reality that's stranger, more beautiful, and more unsettling than anything our ancestors could have imagined. Imagine the surface of the ocean on a calm day. From an airplane high above it looks perfectly smooth, a sheet of blue stretching to the horizon. But descend closer. Fly lower. Soon you begin to see waves, gentle swells, rising and falling in slow rhythm. Lower still, and you see smaller ripples, white caps foam, churning where the wind catches the water. Get close enough right down to the surface, and the ocean is chaos. Droplets spray, bubbles rise and burst. The smooth sheet you saw from above dissolves into turbulent, restless motion. Space-time scientists suggest might be like that ocean, smooth from far away, foaming at the smallest scales. This is the vision that haunted physicist John Archibald Wheeler in the 1950s. Wheeler was a giant of 20th century physics, a man who worked on the atomic bomb, who coined the term black hole, who mentored Richard Feynman and Kip Thorne, and a generation of brilliant minds. But perhaps his most poetic contribution was the idea of quantum foam. In 1955, Wheeler proposed that at the Planck scale, space-time isn't a static stage, but a seething sea of quantum fluctuations, tiny wormholes opening and closing, virtual particles appearing and vanishing, geometry itself writhing and twisting in ways that violate everything we think we know about the smooth continuum of Einstein's relativity. Wheeler called it the quantum foam, and the name stuck. It's an evocative image, isn't it? Space, not as a rigid framework, but as something alive, bubbling, trembling with energy. And the reason for this trembling, research shows, comes from one of the strangest principles in quantum mechanics, the Heisenberg uncertainty principle. You've probably heard of it. It says you can't know both the position and momentum of a particle with perfect precision. The more accurately you measure one, the more uncertain the other becomes. But the uncertainty principle doesn't just apply to particles. It applies to everything, including energy and time. The energy-time uncertainty relation tells us that over very short periods of time, energy can fluctuate wildly. The shorter the time interval, the larger the possible fluctuation. And at the Planck time, about 5 times 10 to the negative 44 seconds, the time it takes light to travel 1 Planck length, the energy fluctuations become enormous. Scientists suggest these fluctuations are so large that they can temporarily create particle-antiparticle pairs out of nothing, borrowing energy from the vacuum itself, as long as they disappear again quickly enough that the universe's bookkeeping doesn't notice. This happens all the time everywhere, even in the empty space between the stars. Virtual particles pop into existence, exist for a fleeting moment, and then annihilate back into the vacuum. We can't see them directly, but we can measure their effects. The Casimir effect, for instance, first predicted in 1948 and measured experimentally in 1997, shows that 2 metal plates placed very close together in a vacuum experience a tiny attractive force. The reason research shows is that the vacuum between the plates has fewer virtual particles than the vacuum outside, creating a pressure difference. The nothing between the plates is less empty than the nothing around them. It's a small effect, a whisper, but it's real. The vacuum hums with hidden energy. But at the Planck scale, these fluctuations don't just create particles, they create fluctuations in space-time itself. Because energy and mass are equivalent thanks to Einstein's E equals mc squared, and because mass curves space-time thanks to general relativity, a large enough energy fluctuation will curve space. And at the Planck energy, the energy concentrated in a Planck volume, scientists suggest the curvature becomes extreme. Space-time doesn't just bend. It twists, kinks, forms tiny loops and handles and bubbles. It becomes foam. Wheeler imagined this foam as a chaotic landscape at the smallest scales. Imagine zooming in on a perfectly flat tabletop. From a distance, it's smooth, but magnify it 1,000,000 times, and you see scratches, dents, imperfections. Magnify it 1,000,000,000 times, and you see the molecular structure, the lattice of atoms. Now, imagine magnifying it all the way down to the Planck scale. Wheeler suggested you'd see a roiling sea of geometry, with tiny wormholes connecting distant points, with space itself constantly changing topology, splitting and merging and flickering in and out of existence. It's not that space is made of foam, it's that at the Planck scale space behaves like foam. One of the most startling implications of quantum foam is that space-time might not be continuous at all. In our everyday experience, you can move smoothly from one point to another. There's no smallest step. You can always take a half step or a quarter step or a thousandth of a step. Distance is a continuum. But if space-time is foamy at the Planck scale, if it's made of discrete quantum events, then maybe there is a smallest step. Maybe space-time is granular, like a digital image made of pixels. Each pixel is one Planck length across, and you can't subdivide it further, because below that scale, the very concept of space dissolves into quantum uncertainty. This idea has profound consequences. If space is discrete, then motion isn't truly continuous. You don't glide smoothly from point A to point B. You hop in Planck-sized jumps too small to notice, but fundamentally different from the smooth trajectories we see at larger scales. Time too might be discrete. Instead of flowing like a river, it might tick forward in Planck time intervals like the frames of a movie. The universe might be less like a symphony and more like a flip book, with each page showing a slightly different configuration of quantum foam. But here's where things get strange. If space-time is foamy, if it's constantly fluctuating, then what does that mean for the concept of distance itself? At scales larger than the Planck length, distance is well defined. You can measure it, you can trust it. But zoom in to the Planck scale and distance starts to shimmer. The shortest path between 2 points might not be a straight line, because space itself is twisting and nodding. The geometry becomes probabilistic. You can only talk about average distances, probable distances, not definite ones. Wheeler loved to think in pictures and thought experiments. He once asked, what if you tried to send a signal from one point to another at the Planck scale? You'd expect the signal to travel in a straight line, right? But if space-time is foaming, the signal might take a wild winding path through the quantum fluctuations, bouncing off virtual particles threading through tiny wormholes. The straight line you see at large scales is actually the average of countless Planck scale detours. It's like trying to walk in a straight line through a dense forest. From far away, your path looks straight, but up close, you're constantly weaving around trees, stepping over roots, navigating obstacles. The Planck scale foam is the forest that space-time walks through. Now, here's a common misunderstanding. When people hear about quantum foam, they sometimes imagine it as a kind of substance, a material that fills space. But that's not quite right. The foam isn't in space. It is space at the Planck scale. It's not that there's some foamy stuff occupying the vacuum. It's that the vacuum itself, when examined closely enough, reveals a quantum structure. The smooth, empty space of classical physics is an illusion, an approximation that works at large scales but breaks down at small ones. Another misconception is that quantum foam is purely theoretical, a flight of fancy, with no connection to reality. But research shows that quantum foam, or something like it, must exist if both quantum mechanics and general relativity are correct. Quantum mechanics says energy fluctuates. General relativity says energy curves space-time. Put those two facts together, and you inevitably get fluctuations in space-time itself. The foam isn't optional. It's a prediction, a consequence of our best theories. The question isn't whether it exists, but what form it takes and how we might detect it. Detecting quantum foam is extraordinarily difficult because the effects are so small. But scientists have proposed clever experiments. One idea involves looking at light from distant gamma-ray bursts, some of the most violent explosions in the universe. If space-time is foamy, if photons traveling through it are constantly being jostled by quantum fluctuations, then light of different wavelengths might travel at slightly different speeds over cosmic distances. Red light and blue light would arrive at Earth at slightly different times, even though they were emitted simultaneously billions of years ago. So far, research shows we haven't detected this effect, which tells us that if quantum foam exists, it's even subtler than some models predicted. Another approach involves measuring the positions of objects with incredible precision. If space itself is jittery at the Planck scale, then the position of an object should fluctuate slightly, even if it's perfectly still. But the fluctuations would be so tiny on the order of the Planck length that no current technology can measure them. You'd need a ruler sensitive enough to detect changes smaller than an atom by a factor of a trillion. We're not there yet. But physicists dream of such instruments, interferometers stretching across continents, gravitational wave detectors, so sensitive they can hear the universe breathing. Wheeler died in 2008 at the age of 96, having spent his life thinking about the deepest questions in physics. He never saw direct evidence of quantum foam, but he believed in it not because he had proof, but because the logic of the theories demanded it. He once said that the universe is a participatory universe, that observers and observations are woven into the fabric of reality, that there's no such thing as a purely objective view from nowhere. The quantum foam in a way embodies that idea. It's the place where the observer and the observed blur together, where measurement and reality become inseparable, where the act of looking changes what you see. There's something almost poetic about the idea of quantum foam. Space isn't dead. It's not a passive container. It's alive with possibility, trembling with energy, constantly creating and destroying, building and unbuilding, at scales too small for us to see, but fundamental to everything we are. Every atom in your body, every thought in your mind, rests on this foundation of seething quantum chaos. The stability we experience, the solidity of the world, is an emergent property, a statistical average over countless Planck scale events. The ground beneath your feet is foaming, but the foam is so fine, so rapid that it averages out to something we call solid. And here's where the lesson deepens. The smoothness we perceive is a lie, but it's a useful lie. It's the lie that lets us navigate the world, that lets us build bridges and fly airplanes and predict the motion of planets. The quantum foam doesn't invalidate the smooth geometry of Einstein's spacetime. It just shows that the smooth geometry is an approximation valid at large scales, but incomplete at small ones. Truth, it seems, is scale-dependent. What's true at one level might not be true at another. The universe speaks different languages at different scales, and part of the challenge of physics is learning to translate between them. Can you imagine what it would be like to experience space-time at the Planck scale? To feel the geometry shifting beneath you, to watch distances stretch and contract, to see the fabric of reality tearing and mending itself in every instant. It would be like standing on an ocean during a storm, but the waves aren't made of water. They're made of space and time themselves. You wouldn't fall down. You'd fall through or up, or sideways into dimensions that don't have names. Causality itself might dissolve. Past and future might become interchangeable. The very concept of here and now might lose all meaning. Of course, you can't experience it, not directly. Your body, your neurons, your consciousness all operate at scales billions of times larger than the Planck scale. The foam is hidden from you by sheer magnitude, buried beneath layer after layer of emergent structure. But it's there, underneath everything, the trembling foundation on which the universe rests. And knowing it's there changes how you see the world. The floor you're standing on, the air you're breathing, the light falling through the window, all of it resting on a sea of quantum uncertainty, stable, only because the fluctuations are so small and so fast that they cancel out, leaving behind the illusion of permanence. Wheeler's quantum foam is more than a scientific idea. It's a shift in perspective, a reminder that reality is stranger than it appears, that the calm surface hides depths we can barely fathom, and that at the very smallest scales at the Planck length, the universe isn't just uncertain, it's unimaginably beautifully wild. But wildness at the Planck scale doesn't exist in isolation. It connects to other mysteries, other scales, other ideas. Because if space-time foams at the smallest distances, what happens at the boundaries of the largest objects we know? What happens where gravity becomes so strong that space-time curves into itself and nothing, not even light, can escape? What happens at the edge of a black hole where the Planck scale and the cosmic scale finally meet? Black holes are where the universe folds in on itself, where space-time curves so severely that it tears, creating a boundary from which nothing, not even light, can return. They're the cosmic endpoints, the places where matter collapses to such extreme density that all the normal rules break down. And at the heart of every black hole hidden behind the event horizon lies a singularity, a point of infinite density, a place where the mathematics screams. And it's at this edge, this threshold between the knowable and the unknowable, that the Planck length whispers its secrets most clearly. The story of black holes and the Planck scale begins in the early 1970s with a young graduate student named Jacob Bekenstein. Bekenstein was studying under John Wheeler, the same Wheeler who dreamed of quantum foam, and he was troubled by a problem. Black holes seem to violate the second law of thermodynamics. The second law says that entropy, the measure of disorder in a system, always increases. Throw a book into a fire, and its organized information turns to random heat and ash. Entropy goes up. But what happens if you throw a book into a black hole? The book vanishes behind the event horizon. Its entropy seems to disappear from the universe. The second law appears to break. Bekenstein proposed something radical. He suggested that black holes themselves have entropy, that they carry information somehow encoded on their surface. And crucially, he proposed that the entropy of a black hole is proportional not to its volume, as you might expect, but to the area of its event horizon. The bigger the surface, the more entropy. This was strange. Stranger still, when you calculated the proportionality constant it involved the Planck length. Specifically, research shows the entropy of a black hole is proportional to the area of its event horizon divided by the square of the Planck length. The Planck scale, it seemed, was the natural unit for counting the information capacity of space-time itself. At first, physicists were skeptical. Black holes having entropy information encoded on surfaces. It sounded too abstract, too divorced from physical reality. But then, in 1974, Stephen Hawking published a paper that changed everything. Using quantum field theory in curved space-time, Hawking showed that black holes aren't completely black. They emit radiation. Thermal radiation with a temperature inversely proportional to their mass. Small black holes are hot. Large black holes are cold. And crucially, this radiation carries entropy. Hawking had proven Bekenstein right. Black holes do have thermodynamics. They have temperature and entropy just like any other physical system. The temperature of a black hole is called the Hawking temperature, and it's extraordinarily small for astrophysical black holes. A black hole with the mass of the sun has a temperature of about 60 billionths of a Kelvin, far colder than the cosmic microwave background. But imagine a tiny black hole one with a mass of just a few micrograms. Research shows such a black hole would be hot, radiating intensely, and it would evaporate completely in a fraction of a second. And the size of such a black hole, about the Planck length. At the Planck scale, black holes and quantum mechanics meet head-on. A Planck mass black hole has a Schwarzschild radius, the radius of its event horizon, equal to the Planck length. It's the smallest black hole that can exist, and it's also the point where quantum gravity effects become dominant. This connection between black holes and the Planck scale suggests something profound. It suggests that space-time itself might have a granular structure with each grain about a Planck area in size. Think of it like this. The event horizon of a black hole is a surface, a boundary in space-time. Bekenstein and Hawking showed that this surface can store information with each Planck area acting like a single bit, a quantum of information. If you wanted to count how much information a black hole can hold, You divide the area of its event horizon by the Planck area. That gives you the maximum number of bits that can be encoded on that surface. This idea led to one of the most surprising concepts in theoretical physics, the holographic principle. Proposed by Gerard 't Hooft and refined by Leonard Susskind in the 1990s, the holographic principle suggests that all the information contained in a volume of space can be encoded on the boundary of that volume. It's as if the three-dimensional universe we experience is actually a projection, a hologram of information stored on a two-dimensional surface. And the fundamental unit of that information? Storage, the Planck area. It sounds like science fiction, doesn't it? That the entire universe might be a hologram, a shadow cast by information, living on some distant boundary. But the mathematics is compelling. The holographic principle resolves paradoxes about information loss in black holes. It suggests deep connections between gravity and quantum mechanics. And it all hinges on the Planck scale, on the idea that space-time has a fundamental graininess encoded in the Planck length. But black holes aren't the only place where the Planck scale becomes crucial. There's another theory, perhaps the most ambitious in all of physics, that lives entirely at the Planck scale: string theory. In the standard model of particle physics, particles like electrons and quarks are treated as point-like objects with no internal structure. But string theory proposes something different. It suggests that the fundamental constituents of reality aren't particles at all. They're tiny vibrating strings, and these strings are about a Planck length long. String theory emerged in the late 1960s originally as an attempt to describe the strong nuclear force. But by the 1980s, physicists realized that string theory could do something far more ambitious. It could unify all the forces of nature, including gravity, into a single framework. In string theory, different particles are just different vibrational modes of the same fundamental string. An electron is a string vibrating one way. A photon is a string vibrating another way. Gravity itself emerges from strings vibrating in yet another pattern. The reason strings need to be Planck-sized is subtle but profound. Research shows that if strings were much larger than the Planck length, the theory would predict effects we should have already seen in particle accelerators. If they were much smaller, the theory would require energy scales beyond what even the Planck energy allows. The Planck length is the natural size for strings, because it's the scale where quantum mechanics and gravity become equally important. Below that scale, you can't ignore gravity's quantum nature. Above that scale, you can treat space-time as smooth. String theory is beautiful mathematically, but it has a problem. It's almost impossible to test. The energies required to directly observe strings are about 1 trillion times higher than anything we can achieve with current technology, the Large Hadron Collider. The most powerful particle accelerator ever built reaches energies of about 10 trillion electron volts. To probe the Planck scale directly, you'd need energies of about 10 to the 19 billion electron volts. That's the Planck energy, roughly the energy of a mosquito, concentrated into a single particle. Building an accelerator that powerful would require a machine the size of the Milky Way galaxy. So, string theory remains a hypothesis, a mathematical framework that might describe reality, but hasn't been confirmed by experiment. Some physicists love it for its elegance and its ability to unify forces. Others criticize it for being untestable more philosophy than physics. But whether string theory is right or wrong, it points to something important. It points to the Planck scale as the natural meeting ground of the quantum and the gravitational, the place where any complete theory of nature must make its stand. There's another approach to quantum gravity, one that takes a different path, but arrives at a similar destination: loop quantum gravity. Unlike string theory, which treats space-time as smooth at large scales, with strings vibrating within it, loop quantum gravity suggests that space-time itself is made of discrete loops. Imagine space as a fabric woven from threads, each thread about a Planck length long. These threads connect at nodes, forming a vast network called a spin network. Space isn't continuous in this picture. It's granular, made of indivisible quanta of volume and area. In loop quantum gravity, the Planck length represents the size of these fundamental loops. You can't subdivide space beyond the Planck scale because there's nothing smaller to divide. Space is quantized just like energy is quantized in Planck's original insight. And this quantization has consequences. Research shows that in loop quantum gravity, the Big Bang singularity might be replaced by a big bounce. Instead of starting from a point of infinite density, the universe might have contracted to a Planck scale size and then rebounded, expanding outward to form the cosmos we see today. The Planck scale becomes a kind of cosmic cushion, preventing the complete collapse to zero size. Loop quantum gravity, like string theory, is still a work in progress. It makes predictions, but they're hard to test. It resolves some problems like the singularity at the Big Bang, but it introduces others. The two theories, string theory and loop quantum gravity, approach the problem of quantum gravity from opposite directions. String theory starts with particles and builds up to space-time. Loop quantum gravity starts with space-time and breaks it down into quanta. Both rely on the Planck scale. Both suggest that at the smallest distances, reality is fundamentally different from what we experience. Here's a common mistake people make. They hear about these theories and assume one of them must be right, that we just need to figure out which one. But the truth might be more subtle. It's possible that both approaches are capturing different aspects of a deeper truth we don't yet understand. It's possible that the correct theory of quantum gravity will look like neither string theory nor loop quantum gravity, but something else entirely, something we haven't imagined yet. The Planck scale is the signpost pointing toward that theory, but we haven't reached it yet. There's a lesson in this: uncertainty, isn't there? Science isn't about having all the answers, it's about asking better questions. The Planck length didn't give us a complete theory of quantum gravity. It gave us a target, a scale where we know the theory must work even if we don't know what that theory looks like yet. It's a reminder that nature is under no obligation to be comprehensible, but it is astonishingly describable. We can write equations, we can make predictions, we can test ideas even if the tests are indirect, even if they take decades. And the predictions are strange. Black holes that encode information on their surfaces. Strings vibrating in 10 or 11 dimensions, most of which are curled up so small we can't see them. Space-time woven from loops discrete and granular at the smallest scales. These ideas push the boundaries of imagination. They force us to think in ways that feel unnatural, counterintuitive, almost dreamlike. But they all emerge from the same source, from taking the constants of nature seriously, from following the mathematics wherever it leads, from refusing to accept that space-time is simply a given, a background, a stage. At the Planck scale, the stage becomes the actor. Have you ever wondered what it would mean if one of these theories is correct? If space-time really is made of loops or strings? If information really is holographic? What does that say about reality? It says that the universe is far more interconnected than it appears, that the surface and the volume are not independent, that the smallest scales and the largest scales speak to each other across the vast middle where we live. A black hole the size of a galaxy, and a string the size of the Planck length, different manifestations of the same underlying principles. And here's where it gets personal. You are made of atoms, and atoms are made of particles, and particles might be made of strings or loops or something else vibrating at the Planck scale. If that's true, then the deepest structure of your body, the foundation of your existence, is connected to the deepest structure of black holes, of the Big Bang of the cosmos itself. The Planck length isn't some distant abstract concept. It's in you. It's in everything. Hidden, yes. Inaccessible, yes. But fundamental. The ground of being, the theories we've explored, string theory loop, quantum gravity, black hole, thermodynamics, they're all attempts to read the whispers of the Planck scale, to decode the message hidden in the constants, to understand what happens when quantum mechanics and gravity finally speak the same language. We're not there yet, We might not be there for a long time, but the journey itself reveals something beautiful. It reveals that the universe has a structure, layers upon layers, each more subtle than the last, each pointing toward a unity we can sense but not yet touch. And that unity isn't just mathematical, it's philosophical. It suggests that the boundaries we draw between particle and wave, between matter and space, between observer and observed, are provisional, useful at our scale, but dissolving at others. The Planck scale is where those boundaries blur most completely, where everything becomes everything else. But if the Planck scale defines where our theories break down, where the mathematics becomes uncertain, then what does that say about our ability to measure it? What does it say about the very act of observation? Can we ever truly see the Planck length, or does the universe hide it from us by design? There's a paradox hidden at the heart of measurement. The more precisely you want to observe something, the more you must disturb it. This isn't a limitation of technology. It's not something we can fix with better instruments or cleverer designs. It's woven into the fabric of reality itself, a fundamental tension between knowing and being. And nowhere does this paradox become more absolute, more insurmountable than at the Planck scale. The universe, it seems, has drawn a line, a boundary beyond which observation itself becomes impossible. Not difficult, impossible. The story begins as so many quantum stories do with Werner Heisenberg. In 1927, Heisenberg published his uncertainty principle, one of the most profound insights in the history of physics. The principle states that you cannot simultaneously know both the position and momentum of a particle with perfect precision. The more accurately you measure one, the more uncertain the other becomes. This isn't because of clumsy measurement tools. It's because particles don't have definite positions and momenta until you measure them. They exist in a superposition of possibilities, a quantum haze that collapses into a specific state only when observed. The reason for this uncertainty, research shows, is fundamentally tied to the wave nature of particles. To measure the position of an electron, you need to bounce something off it, typically a photon. But photons carry momentum. When a photon hits an electron, it transfers some of that momentum, changing the electron's motion. The shorter the wavelength of the photon, the more precisely you can locate the electron, but the more momentum the photon carries and the more violently it disturbs the electron. You can choose to know where the electron is, or you can choose to know how fast it's moving, but you can't have both. The universe forces you to pick. Now scale this idea down. Imagine you want to measure a very small distance, much smaller than an atom. To do that, you need a probe with a very short wavelength. And thanks to the relationship between wavelength and energy, discovered by Max Planck and refined by Einstein, a shorter wavelength means higher energy. The wavelength is inversely proportional to the energy. So, to probe smaller and smaller distances, you need higher and higher energy photons. This seems straightforward, almost mechanical. Just keep increasing the energy and you can keep looking smaller. But there's a limit. A hard absolute limit imposed not by technology, but by the structure of space-time itself. At the Planck length, scientists suggest the energy required to probe that distance is the Planck energy, about 10 to the 19th billion electron volts. That's an astonishing amount of energy concentrated into a single particle. To put it in perspective, the Planck energy is roughly the energy of a car traveling at highway speed, about 300 joules, squeezed into a region of space about 10 to the negative 35 meters across. The energy density at that scale becomes so extreme that something unexpected happens, something that has nothing to do with quantum mechanics directly, but everything to do with gravity. Einstein's general relativity tells us that energy and mass are equivalent and both curve space-time. The more energy you concentrate in a small region, the more space-time curves. Under normal circumstances, this curvature is negligible. But at the Planck scale, the curvature becomes catastrophic. A photon carrying Planck energy, when confined to a Planck-sized region, creates a gravitational field so strong that it curves space-time into a black hole. The The photon you are using as a probe collapses into a tiny singularity, and instead of measuring the distance, you've created a horizon from which nothing can escape. This is the measurement problem of the Planck scale, and it's not just theoretical speculation. It's a consequence of combining quantum mechanics and general relativity, our two most successful theories. The act of measuring a Planck scale distance requires energy sufficient to create a Planck mass black hole, the very tool you need to see that small destroys the thing you're trying to see, wrapping it in an event horizon and hiding it forever. The universe has built a shield around its smallest scales, a barrier made not of matter, but of geometry itself. John Wheeler, who thought deeply about these things, once called this the ultimate observer effect. In quantum mechanics, observation changes the system. But at the Planck scale, observation doesn't just change the system, it annihilates the possibility of observation. You can't peek behind the curtain because the act of peeking draws the curtain tighter. It's as if the universe is saying, you may wonder what happens here, you may calculate and theorize and dream, but you may not look. Not directly, not ever. There's a beautiful, almost poetic irony to this. The Planck length is defined by fundamental constants of nature. It's not arbitrary. It's not a human invention. It emerges naturally from the interplay of quantum mechanics, relativity, and gravity. And yet, this natural, inevitable distance is also the distance we can never directly measure. It's like the universe has left us a clue, a signpost pointing toward its deepest structure, but written in a language we can read only indirectly through mathematics and inference, never through direct perception. Let's think about this more carefully. Imagine you're a physicist with access to unlimited resources. You want to build a microscope powerful enough to see the Planck length. What would you need? First, you'd need a source of photons with wavelengths on the order of the Planck length. That means photons with Planck energy. To generate such photons, you'd need a particle accelerator. But not just any accelerator. Research shows you'd need one with a circumference roughly equal to the diameter of the Milky Way galaxy, about 100,000 light years. That's already absurd, but let's keep going. Even if you could build such an accelerator, even if you could somehow generate photons with Planck energy, you'd face the black hole problem. The moment you try to focus that photon onto a Planck-sized region to probe it, the energy density becomes so high that a black hole forms. The Schwarzschild radius of a Planck mass black hole the size of its event horizon is exactly the Planck length. So, your probe, instead of illuminating the structure of space-time, would create a tiny gravitational trap. The measurement destroys itself. The observation collapses into singularity. This isn't a technological challenge, it's an ontological one. It's not that we haven't figured out how to measure the Planck length yet. It's that the structure of reality forbids it. The laws of physics themselves conspire to keep the Planck scale hidden. And this raises a profound question. If we can never observe something directly, can we say it's real? Does the Planck length exist as a physical distance, or is it just a mathematical abstraction? A number that falls out of equations but has no counterpart in the actual world? Most physicists would argue that the Planck length is real, even if unobservable. After all, it's constructed from fundamental constants that are themselves measured and verified. Planck's constant, the speed of light, the gravitational constant. These are real numbers describing real aspects of nature. Combine them, and the Planck length emerges as inevitably as a triangle's angles sum to 180 degrees in flat geometry. It's a prediction of the theories and the theories' work. They describe reality with astonishing accuracy. So, the Planck length by extension must describe something real, even if that something lies beyond the reach of direct measurement. But there's a deeper philosophical point here. The Planck length represents the limit of operationalism, the idea that physical concepts are defined by the operations used to measure them. Below the Planck scale, measurement operations break down. You can't define position more precisely than the Planck length because the tools needed to define position at that scale create conditions that destroy the possibility of definition. In a sense, the Planck length is the smallest distance that has operational meaning. Smaller distances might exist in some abstract mathematical sense, but they can't be tied to observations, and without observations, physics loses its anchor. Here's a common misunderstanding. Some people hear that we can't measure the Planck length and conclude that it's irrelevant, that it's just a curiosity with no impact on the real world. But that's not true. The Planck scale sets the boundary conditions for our theories. It tells us where quantum mechanics and general relativity must merge. It guides theorists in their search for a unified theory. It provides a natural cutoff for calculations that would otherwise diverge to infinity. The Planck length isn't just unmeasurable, it's indispensable. Consider the Big Bang. In the standard cosmological model, the universe began in a singularity, a point of infinite density and infinite temperature. But that infinity is a red flag. It signals a breakdown of the theory. Scientists suggest that instead of a true singularity, the Big Bang likely involved a Planck-scale epoch, a brief period when the universe was so small and so dense that quantum gravitational effects dominated. During this epoch, space-time itself was quantum fluctuating and uncertain. The universe wasn't a point. It was a region about a Planck length across seething with quantum possibilities. We can't observe the Planck epoch directly. It happened nearly 14 billion years ago, and the energies involved are far beyond anything we can recreate. But we can infer its existence from the structure of the universe today, from the cosmic microwave background, from the distribution of galaxies, from the subtle patterns imprinted on the sky. Another place where the Planck scale matters, even though we can't measure it, is in the vacuum energy problem. Quantum field theory predicts that empty space isn't really empty. It's filled with virtual particles, fluctuations that appear and disappear on timescales so short that they don't violate energy conservation. These fluctuations contribute to the energy density of the vacuum. But when you calculate how much energy they should contribute, the answer depends on the shortest wavelength fluctuations you include. If you include fluctuations all the way down to the Planck scale, research shows the vacuum energy density comes out to be about 10 to the 120 times larger than what we observe. That's a discrepancy of 120 orders of magnitude, one of the worst predictions in the history of physics. The Planck scale acts as a natural cutoff for these calculations. It tells us that fluctuations smaller than the Planck length probably don't contribute either, because space-time becomes discrete at that scale, or because some unknown physics takes over. We don't know the exact mechanism, but the Planck length provides a boundary, a place to stop the calculation before it runs off to infinity. Without that boundary, our theories would be hopelessly broken. With it, they're merely incomplete, which is much better. So, the Planck length is both unreachable and essential. It's a horizon we can't cross but must acknowledge. It's the edge of the map, marked not with dragons, but with black holes and quantum foam, and the merging of principles that refuse to merge anywhere else. And there's something humbling about that, isn't there? All our technology, all our cleverness, all our ability to split atoms and detect gravitational waves and send probes to the edge of the solar system. None of it can take us to the Planck scale. The universe has reserved that realm for itself. But here's the lesson. Just because we can't measure something directly doesn't mean we can't understand it. Indirect evidence, mathematical consistency. The predictive power of theories, these are all valid ways of knowing. We've never seen an electron directly yet. We know they exist because of countless indirect measurements. We've never visited the core of the sun, yet we know it's fusing hydrogen into helium because of the light that reaches us. The Planck length is similar. We can't probe it with experiments, but we can probe it with logic, with mathematics, with the constraints imposed by the constants of nature. And those constraints are telling us something profound. They're telling us that the universe has structure all the way down, but the deepest structure is hidden, protected by the very laws that govern it. It's as if reality has layers, each accessible in its own way, but with the final layer veiled not by secrecy, but by necessity. To see it would require breaking it, and breaking it would mean losing the very thing we sought to understand. Have you ever felt that way about something in your own life? That the closer you look, the more it eludes you? That some truth can't be grasped directly, but only understood through their effects, their shadows, the traces they leave behind? The Planck scale is like that. It's the truth we know is there, but can never hold. And maybe that's okay. Maybe the universe is allowed to have secrets. Maybe some boundaries aren't meant to be crossed, but to be respected, contemplated, wondered at from a distance. Yet, even if we can't measure the Planck length, we can measure time. And time at the Planck scale is just as strange, just as fundamental. If the Planck length is the smallest meaningful distance, then there must be a smallest meaningful duration. A tick of the cosmic clock so brief that below it, the very concept of before and after dissolves into quantum uncertainty. And that duration, that Planck time, is where the universe's heartbeat lives, hidden but eternal, pulsing at the very edge of existence. Time flows. At least, that's how it feels. Seconds melt into minutes, minutes into hours, hours into the quiet march of days and years and lifetimes. We measure time with clocks, with the swing of pendulums, the vibration of quartz crystals, the oscillation of cesium atoms. Each tick marks a passage, a before and an after, a progression from what was to what will be. But what if time doesn't flow smoothly? What if at the deepest level, time itself is quantized, broken into discrete moments so brief that between them, the concept of duration loses all meaning? What if the universe has a heartbeat, and that heartbeat ticks at the Planck scale? Just as the Planck length emerges from combining the fundamental constants of nature, so too does the Planck time. It's calculated the same way. Take Planck's constant, the gravitational constant, and the speed of light, and combine them in just the right proportion. The result is a duration, 5.39 times 10 to the negative 44 seconds. That's the Planck time. To write it out, you'd put 43 zeros after the decimal point before reaching the 5. It's the time it takes light traveling at its maximum cosmic speed to cross one Planck length. And scientists suggest it represents the shortest interval of time that has any physical significance. To understand how short the Planck time really is, we need comparisons. But the comparisons break down almost immediately because the Planck time exists in a realm so far removed from human experience that our intuitions fail. Let's try anyway. A second is a long time at the human scale. Your heart beats once per second, more or less. You can count seconds, feel them pass. Now, divide that second by 1 billion. You're at a nanosecond, the time it takes light to travel about 1 foot. Computer processors operate on nanosecond timescales. Divide by another billion, and you reach 1/billionth of a second, 10 to the negative 18 seconds. That's an attosecond, the timescale of electron motion within atoms. Attosecond lasers can capture snapshots of electrons orbiting nuclei freezing motion that happens faster than anything we can perceive directly. But the Planck time is 26 orders of magnitude shorter than an attosecond. If an attosecond were stretched to 1 second, the Planck time would still be 100 million times shorter than an attosecond. It's not just small, it's incomprehensibly small. And yet, research shows it might be the fundamental tick of the cosmic clock, the quantum of time itself. The idea that time might be discrete, that it might come in indivisible chunks rather than flowing continuously, is deeply counterintuitive. We experience time as smooth. We don't feel it stuttering or jumping. But at the Planck scale, the smoothness we experience might be an illusion, a statistical average over countless quantum ticks happening too fast for us to notice. It's like watching a movie. On-screen motion appears fluid and continuous, but the film is actually a series of still images 24 frames per second, flickering so quickly that your brain stitches them together into the illusion of movement. If time is quantized at the Planck scale, then the universe might be like that movie, a series of frozen snapshots advancing frame by frame, with each frame separated by a Planck time interval. The notion of discrete time has profound implications. If time comes in quanta, then there's no such thing as an event that happens between two Planck time intervals. There's no such thing as half a Planck time or a tenth of a Planck time. Below that scale, the concept of when becomes meaningless. You can't ask what happened at 10 to the negative 45 seconds because there's no clock that can measure such an interval. The universe itself doesn't have the resolution. It's as if reality has a frame rate, and the Planck time is the inverse of that rate. 1 frame per 5.39 times 10 to the negative 44 seconds. The fastest possible frame rate allowed by the laws of physics. This idea connects directly to the Planck length. If space is quantized, if the Planck length is the smallest meaningful distance, then it makes sense that time would be quantized too. After all, space and time aren't separate entities. Einstein's relativity taught us that they're woven together into a single fabric called space-time. What happens in space affects what happens in time, and vice versa. If space has a minimum unit, a pixel size, then time should have a corresponding minimum unit, a frame duration. And the relationship between them is set by the speed of light. Light travels 1 Planck length in 1 Planck time. It's the cosmic speed limit meeting the cosmic resolution limit. The history of thinking about time quanta goes back decades, though it's never been as popular as thinking about space quanta. In the 1930s, physicists like Leon Rosenfeld speculated that time might not be infinitely divisible, that there might be a smallest interval below, which the notion of time breaks down. But these ideas remain speculative, difficult to formalize, even harder to test. It wasn't until the development of quantum gravity theories in the late 20th century that the Planck time became central to the discussion. In loop quantum gravity, for instance, time is treated as emergent rather than fundamental. At the Planck scale, there is no universal time ticking uniformly across the universe. Instead, time arises from the relationships between quantum events, from the way spin networks evolve and interact. The Planck time isn't the tick of a clock. It's the time scale at which those interactions happen, the natural rhythm of quantum geometry. In this picture, asking what happened before the Planck time is like asking what's north of the North Pole. The question doesn't make sense because the framework that gives meaning to before and after breaks down. String theory takes a different approach but arrives at a similar conclusion. In string theory, the fundamental objects are strings vibrating in multiple dimensions, and those vibrations have characteristic frequencies. The highest frequency vibrations occur on the Planck time scale. Below that, research shows the concept of time as a smooth parameter loses coherence. The strings themselves don't experience time in the classical sense. They exist in a more abstract space where time and space are interchangeable coordinates. And only at larger scales does time emerge as the dimension we perceive flowing forward. But whether time is truly discrete or merely appears discrete at the Planck scale is still an open question. Some physicists argue that time remains continuous even at the Planck scale, but that our ability to measure it, to define what we mean by a moment, breaks down. Others argue that time is fundamentally grainy, that the Planck time represents a true quantum of duration. The difference is subtle but important. In the first case, time exists below the Planck scale, but we can't access it. In the second case, time simply doesn't exist below the Planck scale. There's nothing to access because there's no there. One of the most fascinating applications of Planck time is in cosmology, particularly in understanding the Big Bang. In the standard model of cosmology, the universe began about 13.8 billion years ago in an event of unimaginable density and temperature. As we trace the history of the universe backward, the density and temperature increase. At 1 second after the Big Bang, the universe was hot enough for nuclear fusion to occur, creating the first light elements like helium. At 1 millisecond, quarks were still free, not yet bound into protons and neutrons. At 1 microsecond, the universe was a soup of fundamental particles, radiation, and energy. But keep going back. At 10 to the negative 12 seconds, the electroweak force, which today appears as two separate forces, electromagnetism and the weak nuclear force was still unified. At 10 to the negative 35 seconds, the universe underwent a period of exponential expansion, called inflation, growing from subatomic size to macroscopic size in a fraction of a second. And then, at 10 to the negative 43 seconds, we reach the Planck epoch. This is the earliest moment we can meaningfully discuss with our current physics. Before the Planck time, scientists suggest the universe was so small and so dense that quantum gravitational effects dominated completely. Space-time itself was quantum fluctuating wildly with no clear distinction between space and time, matter and energy, cause and effect. The Planck epoch lasted only one Planck time, about 5 times 10 to the negative 44 seconds. During that instant, the entire observable universe, everything that would eventually become hundreds of billions of galaxies, was compressed into a region about 1 Planck length across. The temperature was the Planck temperature, about 10 to the 32 Kelvin, hot enough that all forces were unified, all particles indistinguishable. It was the ultimate singularity, the point where our theories give up and admit defeat. We can't describe what happened during the Planck epoch because we don't have a theory of quantum gravity. General relativity and quantum mechanics are 2 pillars of understanding, both break down at those scales. But we can say that whatever happened, it happened fast. The Planck time is the duration of that epoch. In less time than it takes light to cross the nucleus of a hydrogen atom, by a factor of 10 to the 24, the universe transitioned from quantum chaos to something describable by classical physics, or at least by physics we can begin to understand. After the Planck epoch, the universe began to cool and expand. Space-time became smooth or smooth enough that Einstein's equations started to work. Particles began to differentiate. Forces began to separate. Time began to flow in the way we recognize, with a clear arrow pointing from past to future. But that first instant, that Planck time, remains shrouded in mystery. It's the moment of creation, the birth of everything. And it happened on a time scale so brief that calling it an instant feels like an overstatement. There's a common mistake people make when thinking about the Big Bang and the Planck time. They imagine the Big Bang as an explosion in space with matter flying outward from a central point. But that's not right. The Big Bang was an explosion of space itself. There was no center. There was no outside. Space itself expanded, carrying matter along with it. And at the Planck epoch, space wasn't just small. It was fundamentally different quantum in nature, not yet the smooth continuum we inhabit today. The Planck time marks the transition from that quantum proto-reality to the classical universe we can describe with equations. Think about what this means for the concept of time. Before the Planck epoch, there might not have been time at all, at least not in the way we understand it. Time might have been a quantum variable entangled with space, uncertain, fluctuating. The Planck time might mark the moment when time became time, when the ticking of the cosmic clock began. Before that, there was no before. There was only a quantum superposition of possibilities, a state from which the universe emerged not through a process, but through a quantum event. This is where the idea of the universe's heartbeat becomes almost poetic. If the Planck time is the shortest duration that has meaning, then it's the rhythm underlying all other rhythms. Every oscillation, every vibration, every tick of every clock, from the rotation of pulsars to the decay of radioactive atoms to the beating of your heart, is built on a foundation of Planck time intervals. The universe doesn't tick at the Planck scale in the sense that we can hear it or measure it, but the Planck time sets the ultimate tempo, the fastest beat, the highest note in the cosmic symphony. Here's another way to think about it. Imagine reality as a vast computation, a kind of cosmic algorithm running on the hardware of space-time. Each step of the computation takes 1 Planck time. Each bit of information occupies 1 Planck area. The universe processes information at the Planck scale, updating its state frame by frame, calculating the next moment from the previous one. We don't experience these frames because they happen far too quickly. but they're there underlying everything. Research shows that some physicists, particularly those working on digital physics and computational models of the universe, take this idea seriously. They suggest that the universe might literally be a computer, and the Planck time and Planck length are its clock speed and pixel size. Whether or not the universe is a computer is still a matter of debate, but the idea captures something important. The Planck time represents a fundamental limit on how finely we can divide time, just as the Planck length represents a limit on how finely we can divide space. Together, they define the resolution of reality. And that resolution, while unimaginably fine, is not infinite. Reality has a grain of texture, a structure at the smallest scales, and that structure is written in the language of the constants h, c, and g, the trinity that defines the Planck units. So, what does it mean to live in a universe with a Planck time? It means that all change from the drift of galaxies to the firing of neurons in your brain happens in discrete steps, even if those steps are too small to perceive. It means that the smooth flow of time we experience is an approximation, a coarse graining over countless quantum ticks. It means that the universe has a rhythm, and that rhythm is set not by human convenience, but by the deepest laws of physics. And here's the final thought. The Planck time is the same everywhere. It doesn't matter if you're on Earth, or orbiting a black hole, or floating in the emptiness between galaxies. The Planck time is constant, universal, unchanging. It's one of the few truly absolute quantities in a universe otherwise governed by relativity, where time can slow down, speed up, dilate, contract. But the Planck time built from fundamental constants is the same for all observers. It's the heartbeat that connects everything, the tick, that echoes through every corner of the cosmos, unifying the smallest and the largest, the fastest and the slowest, the beginning and the end. And now, having descended as far as we can go, having reached the limits of space and time, what remains? What can we say about a universe that hides its deepest truths behind horizons of measurement and thresholds of meaning? Perhaps the answer lies not in what we can measure, but in what we can imagine in the edges of the map where certainty fades and wonder begins. We have traveled far tonight, from the space between your fingers to the space between galaxies and then inward down through layers of reality most people never think about. Through cells and molecules, through atoms and nuclei, through quarks and the quantum foam, all the way to a distance so small it barely qualifies as a distance at all. 1.6 times 10 to the negative 35 meters. The Planck length, the shortest meaningful measure in the universe. And along the way, we've met the people who discovered it not by seeing it, but by thinking deeply about what the constants of nature were trying to say. Max Planck didn't know he was opening a door to the smallest scale when he solved the problem of black body radiation in 1900. He was just trying to make the mathematics work, trying to explain why hot objects glow the way they do, without predicting infinite energy at high frequencies. His solution that energy comes in discrete packets in quanta was something he called an act of desperation. He didn't believe it himself, not at first. But from that desperation emerged a constant h, and from that constant combined with the speed of light and the gravitational constant emerged a length, a natural unit built into the fabric of reality. Planck died in 1947 without ever seeing direct evidence of the scale that bears his name, but his legacy lives on in every quantum experiment, every particle accelerator, every attempt to understand the structure of space-time. We've learned that the Planck length isn't just a number, it's a meeting point. The place where three pillars of physics, quantum mechanics, relativity, and gravity all converge. Quantum mechanics with its uncertainty and its wave-particle duality encoded in Planck's constant. Relativity with its fusion of space and time, its cosmic speed limit encoded in the speed of light. And gravity, the curvature of space-time by mass and energy encoded in Newton's gravitational constant. These three aspects of reality, usually treated separately, come together at the Planck scale. And when they come together, something extraordinary happens. The smooth geometry of space-time dissolves into quantum foam. Distance becomes uncertain. Time becomes grainy. The universe reveals that beneath its calm surface lies a churning sea of possibility. John Wheeler gave us the image of that foam in the 1950s, a vision of space-time at the Planck scale, as a bubbling, frothing chaos, with virtual particles appearing and vanishing, with tiny wormholes opening and closing, with geometry itself twisting into shapes that defy imagination. Wheeler was a dreamer, but he was a rigorous dreamer. He understood that if quantum mechanics and general relativity are both correct, then quantum foam isn't optional, it's inevitable. The energy-time uncertainty principle guarantees that the vacuum isn't empty, that it hums with fluctuations. And at the Planck scale, those fluctuations are strong enough to warp space-time itself. We can't see the foam directly. We might never see it. But the logic of the theories demands it exist. And we've explored the implications of the Planck scale for some of the strangest objects in the universe. Black holes, where gravity becomes so strong that space-time curves into itself, creating an event horizon from which nothing can escape. Jacob Bekenstein and Stephen Hawking showed us in the 1970s that black holes aren't just gravitational prisons. They are thermodynamic objects with temperature and entropy. And the entropy of a black hole, the measure of its information content, is proportional to the area of its event horizon, divided by the Planck area. Each Planck-sized patch on the horizon encodes one bit of quantum information. The Planck length in this picture is the fundamental unit of information storage in the universe. And this led to the holographic principle, the astonishing idea that all the information in a volume of space can be encoded on the boundary of that volume, that the three-dimensional world we experience might be a projection of two-dimensional information living at the Planck scale. String theory and loop quantum gravity, two of the most ambitious attempts to unify quantum mechanics and gravity, both place the Planck length at their core. In string theory, fundamental particles are tiny vibrating strings about a Planck length long, and different vibrations correspond to different particles. The universe in this view is a symphony played on Planck scale instruments. In loop quantum gravity, space-time itself is woven from loops each about a Planck length in size, connected in a vast network. Space isn't continuous but granular, and the Planck length is the size of the grain. These theories are speculative, unproven, perhaps unprovable with current technology. But they're not arbitrary. They're guided by the constants, by the Planck scale, by the conviction that the universe has a fundamental structure, and that structure is written in the smallest possible units. We have also confronted a profound limit. The Planck length can't be measured directly. To see something that small, you'd need a probe with energy so high, it would collapse into a black hole. The very act of measurement destroys the possibility of measurement. The universe has drawn a line, not out of malice, but out of necessity. And that line says, beyond this point. Observation in the classical sense is impossible. You may calculate, you may theorize, you may dream, but you may not look, not directly. And there's a strange beauty in that, isn't there? The universe doesn't owe us transparency. It doesn't promise that every question has an observable answer. Some truths live only in the mathematics whispered between equations, felt rather than seen. And then there's time. The Planck time, 5.39 times 10 to the negative 44 seconds. The duration it takes light to travel one Planck length. If the Planck length is the pixel of space, the Planck time is the frame of time. It's the shortest interval that has meaning, the tick of the cosmic clock, the heartbeat of the universe. At the Big Bang in the first Planck time, after creation, the universe was pure quantum chaos. Space and time were not yet distinct. The forces were unified. Everything that would become stars and galaxies and you was compressed into a region one Planck length across, hotter and denser than anything we can imagine. That moment, that instant, is the origin of everything. And it happened faster than fast, briefer than brief, on a time scale that makes an attosecond look like an eternity. So, where does this leave us standing at the edge of what can be known? The Planck length and Planck time aren't just scientific curiosities. They're fundamental limits, boundaries etched into reality by the constants themselves. They tell us that the universe has a resolution, a grain of texture at the smallest scales. And they tell us something else, something subtler. They tell us that the universe is unified in ways we're only beginning to understand. The smallest distance and the largest structures, the briefest instant and the age of the cosmos, they're connected. Not obviously, not simply, but deeply. Through the constants, through the mathematics, through the fabric of space-time itself. Research shows that we're living in an extraordinary time. For most of human history, people had no idea that space and time were quantized, that there was a smallest scale, that the constants of nature pointed to something fundamental. It took Max Planck's insight, Einstein's relativity, Heisenberg's uncertainty principle, Hawking's black hole thermodynamics, Wheeler's quantum foam, all building on each other, refining each other, pushing the boundaries of what we could understand. And now, more than a century after Planck's first breakthrough, we're still grappling with the implications. We still don't have a complete theory of quantum gravity. We still don't know exactly what happens at the Planck scale, but we know it matters. We know it's there. And we know that understanding it might be the key to understanding everything. There's a lesson in this journey, isn't there? The Planck length started as a mathematical consequence, a number that fell out of an equation. It wasn't discovered through observation. It was revealed through logic, through the interplay of constants, through the relentless application of mathematics to the physical world. And that tells us something important about how we learn. Not everything can be seen. Not everything can be touched. But if the logic is sound, if the mathematics is consistent, if the predictions align with what we observe at larger scales, then we can trust that we're glimpsing something real. The Planck length is real, even if we can never measure it. It's as real as the constants that define it. And here's where it gets personal. You listening to this are made of atoms, and atoms are made of particles. And particles, according to some theories, might be made of strings or loops vibrating at the Planck scale. If that's true, then the deepest structure of your body, the foundation of your existence, is tied to the Planck length. You are built on quantum foam. Your thoughts, your memories, your heartbeat, all rest on a foundation of space-time that's seething and fluctuating at scales far too small to perceive. The solidity you feel, the continuity you experience is an emergent property, a statistical average over countless Planck scale events. You are in a very real sense a pattern in the foam. And so, is everything else. Think about the scale of what we've discussed. From human size, about 1.7 meters down, to the Planck length 10, to the negative 35 meters. That's a journey across 37 orders of magnitude. If you could somehow shrink yourself down passing through each scale, you'd witness transformation after transformation. The biological giving way to the chemical giving way to the atomic giving way to the nuclear giving way to the quark, and then finally the quark giving way to whatever lies at the Planck scale. Strings, loops, foam, something we haven't imagined yet. Each layer more abstract, more mathematical, more divorced from everyday intuition. But each layer no less real. And the journey upward is equally astonishing, from the Planck length to the size of the observable universe about 10 to the 27 meters. That's 62 orders of magnitude. The Planck length sits at the center of that range, equidistant in logarithmic space between the quantum and the cosmic. It's the pivot point, the fulcrum, the scale, where the very small and the very large finally speak the same language. And that language is the language of constants. Planck's constant, the speed of light, the gravitational constant. 3 numbers that don't change no matter where you are, no matter when you measure them. 3 numbers that define not just the Planck scale, but the entire structure of physical law. Have you ever looked up at the night sky and felt small, felt the vastness pressing down on you, the realization that you are a tiny speck on a tiny planet, orbiting a typical star in an ordinary galaxy among hundreds of billions? That feeling is humbling. But here's another way to think about it. You're also vast. Compared to the Planck scale, you're enormous. You contain about 10 to the 28 Planck volumes. That's 100 billion tiny regions of space-time, each one flickering with quantum possibility. You are, in that sense, a universe unto yourself, made of particles that might be strings, animated by forces that emerge from symmetry, breaking in the first moments after the Big Bang, thinking thoughts that depend on neurons firing in patterns shaped by evolution over billions of years. You are connected to the Planck scale and to the cosmic scale. You are the bridge between them. The Planck length doesn't answer all our questions. It raises new ones. What is space-time really made of? Is it continuous or discrete? Is it fundamental or emergent? What happened at the Big Bang before the Planck epoch? Can we ever develop a theory of quantum gravity that works? Will string theory or loop quantum gravity or some other approach win out? Or will the answer be something we haven't thought of yet? These questions remain open. They might remain open for decades, maybe centuries. But the fact that we can ask them, the fact that we've narrowed the mystery down to a specific scale, to a specific set of problems, is itself remarkable. We've mapped the territory of the unknown. We know where the dragons live, even if we can't fight them yet. So, what do we take away from this? What does it mean to know about the Planck length? It means understanding that the universe has structure all the way down, that there's no arbitrary stopping point, no place where the question why becomes meaningless. It means recognizing that the constants of nature are not random but deeply interconnected, pointing to a unity we're still trying to uncover. It means appreciating that some of the deepest truths about reality are accessible not through our senses, but through our minds, through mathematics, through the patient application of logic to observation. And it means accepting that there are limits, not limits to curiosity, not limits to imagination, but limits to measurement, to certainty, to the knowability of all things. The Planck length is a reminder that the universe is both more orderly and more mysterious than it appears. More orderly because the constants define natural units that don't depend on human choices. More mysterious because those units point to scales we can never directly explore. It's the edge of the map, and edges are where the interesting things happen. Edges are where certainty meets wonder, where knowledge meets humility, where the known world fades into the unknown and we're left with questions more beautiful than any answer. We've walked through quantum foam and black hole entropy. We've stood at the Big Bang and touched the limits of measurement. We've met the people who dreamed these ideas into existence, who followed equations into the dark and found light. And now, here we are, at the end of the journey, or maybe not the end, maybe just a resting place. Because the search for understanding doesn't end with the Planck length. It begins there. It's the foundation on which future theories will build, the horizon toward which explorers will always travel even if they never arrive. The universe has its secrets, and maybe some secrets are meant to stay small, hidden not out of cruelty, but out of elegance. Because if we could measure everything, if we could know everything, if there were no mysteries left, what would we have to wonder about? The Planck length gives us something to wonder about. It gives us a question that might never be fully answered, but will always be worth asking. And in that question, in that reaching toward the unknowable, we find something essentially human: the desire to understand, the courage to imagine, the humility to admit that we don't know, and the hope that maybe someday we will. Thank you for drifting with me through this quiet journey to the smallest distance in the universe, for staying curious, for listening, for wondering. The cosmos is vast and it's full of stories, some told in starlight, others in the hum of particles too small to see. And there are more stories waiting, more mysteries to explore, more nights to spend together, letting science whisper its secrets softly. Until then, sleep well, dream gently, And know that the universe in all its strangeness and beauty is always there, breathing quietly at every scale from the infinite to the infinitesimal. Good night.